Okay, got that out of the way. You feel all right about it? Not bad? Once you know the triangles, you know the chart. Once you know the chart, you know the circle. Okay? Even if you don't know the circle, right? Just count by 30s. Count by 45s. So, sine and cosine functions. Here we go. We started talking about it yesterday, where it said, well, what's the sine of 0? What's the sine of pi over 2? What's the sine of pi? What's the sine of 3 pi over 2? And it turns out it kept ping-ponging back and forth and back and forth and back and forth and back and forth because that unit circle, sine values are the y values, and they go from -1 to 0 to 1, and then back down 0 to -1, and then back up 0 to 1 to 0 to -1. The sine values as they go around that circle, if I were to take that circle and stretch it out in terms of angle input, ratio output, it makes that graph. Okay, a sine wave. You probably first heard about these in physical science, talking about electromagnetic radiation. They will find sine or follow sinusoidal curves. Also, that's the official term for sine and cosine waves because it's fun to say. Sinusoidal. Sinusoidal, right? The biggest part of it is that, okay, right above that, it has all the analysis to it, right? You're going to have a domain of all real numbers. I can take the sine of any angle I want, but the range, we saw that the other day. Well, because my range of sine values is only from -1 to 1, y'all got a calculator, or you should have a calculator. Try taking the arc sine of 1.1. You can't do it. That is where we're going to get our fourth commandment of domain finally. You can't take the arc sine or arc cosine of something whose absolute value is greater than 1. Because if it is, you got to remember what sine and cosine are. If sine, come on Frank, if sine of an angle is opposite over hypotenuse, and if that's greater than 1, say it's like 1.1 to 1, you just said that in this triangle, this is 1.1 and this is 1. Why does that just not work? Triangle proportionality theorem. The largest side is always across from the largest angle. 90 is going to be the largest angle in a right triangle, so that's impossible by the definition of the triangle. So that's why all of our sine and cosine values have to be between -1 and 1. That's when we get our arc functions in a few days. We're going to have that domain restriction. Now, a couple of other bits of terminology here. Oh, you can define things by sets. You look above this and it asks, what are the x-intercepts? And the x-intercepts are pi n, where n is an integer. Because the x-intercepts literally happen every pi. Okay, so my x-intercepts might not be a specific value. Instead, they're going to be a set of values, in this case, infinite set. I can do the same thing for maximums. If it starts at pi over 2, 1, and now it's at 5 pi over 2, 1, and then it's back here at -3 pi over 2, 1, then I can say that my maximum is pi over 2 plus 2 pi n, because it's going to keep going in iterations of 2 pi. And that's where we develop the idea of a period. A period of a function, a period of anything, is how long does it take for the cycle to repeat itself. Okay? In a given period of time, they're saying between here and here. Because after that period of time, it's going to repeat itself. The thing's going to happen again. Okay? Specifically for sine and cosine, the period is 2 pi, because that is one full revolution around the circle. After 2 pi, it's just going to start repeating itself. All the values are going to do the same thing in the same order. You can leave that back open again. I notice when the door is closed, it echoes more in here, and I don't like that. So, I want you to look at sine starting at 0 like that. See if it'll actually work here if I try to drag it. Ooh, close. What could you say about cosine then, when I try to overlap those two? Look at the features of it. Pi over 2 translation of sine. Specifically, why would pi over 2 be the translation from sine to cosine? We've talked about it before. Why do sine and cosine switch on my chart with 30 and 60? Getting warmer. We're dancing around it. What are 30 and 60? What's a name for angles 30 and 60? Because they are complementary angles. Because they are complementary angles, that's why it's called the cosine, because they add up to 90. 90 is pi over 2. That's why the sine values of 1 are the pi over 2 translation of the cosine values of it instead, because those are related by that complementary value. So I look at cosine. Instead of starting at 0 and then up, middle, down, middle, up, middle, down, middle, I'm going to start at the maximum, because if you look at your unit circle now, you're talking about the x values. The x values at 0 is 1. And then it gets smaller, goes negative. And then it hits pi and starts coming back up. Because now, instead of going from -1 to 1, y-axis, I'm going from -1 to 1, x-axis. That starts to get, I saw a couple of you printed out that big cheater chart, right? That's why my arc sine values are defined from -pi over 2 to pi over 2, and my arc cosine values are from 0 to pi, because they're the y and x axes respectively. Okay. Notice that the x-axis is labeled in terms of pi. That's why kids tend to get grumbly at chapter 4. You're going to have to graph something. It's going to have to be in terms of pi, which your calculator will not do for you, and those are often in fractions. What happens when we change the period of this thing and every one of these marks becomes 5 pi over 12 apart? You have to fraction. Okay. Notice that in the period of 2 pi, they have 1, 2, 3, 4 spaces. In the period of pi, they have 1, 2, 3, 4 spaces. And those represent maximum, intercept, minimum, intercept, maximum. Basically, those are the relevant features of the graph. So I'm going to graph based on those relevant features. Even though in the middle, I could say, what is the cosine of pi over 4? And it's square root of 2 over 2. You don't want to clutter up your graph with a bunch of radicals. So you only graph like the points that are relevant, meaning easy to do. Then you fill in the dots. If you liked, there were some of you that when we did our quadratics, you just always did 1, 1, up 3, up 5, up 1, up 3, up 5, because they were successive odds. And then if there was a scale factor to it, say it was 3/4 x squared plus blah, 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 all you did was on your y-axis, you said by 3/4. So you could always make the same graph. We're going to apply that concept to these so that we don't have to fit this ugly graph with all these fractions and pies to a nasty scale. I'm just going to change the scale so it makes sense for me. So, starting at the beginning. Oh yeah, other stuff about it. Boy, this should look familiar. Take a look at those two lines. What does that look an awful lot like? Yep. Except because sinusoidal functions are so prevalent, because they happen with particle physics, because they're special. They get special names. Where, yeah, A is my vertical stretch, but we're going to call it the amplitude. Remember that one? Amplitude modulation. Pump more power into it. Okay. B, notice how it's not separated from the x? That happened. I'm going to use B to find the period. 2 pi over B is going to be the period. It tells me how long it takes for this thing to start repeating itself. Remember how we would normally take B and then x plus C over B? We would separate that out for our transformations. Well, they kind of leave it like this, and then they take that into account by saying, instead of a horizontal translation, now it's called a phase shift. A phase shift is negative C over B, which is just if I had factored that out. Okay? And D, instead of calling it a vertical translation, they call it a vertical shift. So it's all the same stuff we've done with transformations. It's just they get special new names. Okay, like y'all seen Second Crudes? I live in animated movie hell. Okay, like what do we need to go save the men from the punch monkeys? New tribe names, and then they all get smacked with paint, and then they ride spider wolves and stuff. It's great. Watch the movie; it's fun. These things are special, so they get special names. It does the same stuff that we've been doing. Okay? So when you look down here, you see the whole stretch compression thing. You see the reflection and knot. Same business. New names. So we're going to describe how the graph sine of x and 1/4 sine of x are related. Find the amplitude. Sketch two periods of both functions on the same coordinate axes. So you got just kind of a blank grid paper ready to go. The first thing I'll do is I will label my axes right now. You see how there's nothing in the B spot or C spot? They're going to start nice with you. They're not going to phase shift. They're not going to change the period or frequency. So that means these are all going to start with green. They're all going to start with a period is from 0 to 2 pi. From 0 to negative 2 pi. Okay? That is the period of a sine and cosine function until I mess with it. The relevant features in between there, this is something that the book doesn't talk about. I have never seen a book talk about this. I call them my quarter marks. My quarter marks are just 1/4 the period. So if the period was 2 pi, take that times 1/4, pi over 2 increments. That tells me each of the boxes on here are going to be by pi over 2. And if you go back to the first page, look at the parent graph, it went by pi over 2. Because that's where the relevant features are. Look at your quadrantal angles on the unit circle. 0, pi over 2, 2 pi over 2 is pi, 3 pi over 2, 4 pi over 2. That's where the fun stuff happens, maximum, minimum, intercept. So in between 0 and 2 pi, you see it's 4 chunks broken up. You go by pi over 2, 2 pi over 2 is pi, 3 pi over 2. It says to make 2 periods of it, so it's customary to make one positive, one negative. Negative pi over 2, negative pi, negative 3 pi over 2. My y-axis, I get to label it however I want. The amplitude of the parent function is 1. So I know it's got to ping back and forth between 1 and negative 1. But g of x, its transformation, the amplitude is 1/4. So I know that I'm going to need to ping pong between 1 and negative 1, between 1/4 and negative 1/4. So I'm actually going to put my 1 and negative 1 here. Because then 1/4 is half a box instead of 1/4 of a box, where it's really, really hard to see. Okay? And then the relevant features. Y equals sine of x. What is the sine of 0? 0. What's the sine of pi over 2? Uno. What's the sine of pi? 0. What's the sine of 3 pi over 2? Negative 1. Sine of 2 pi? 0. You see the pattern, and that's going to be kind of our little mantra. If we put it on auto tune, we'll make $1 million. Okay? It's not what is the sine of this, it's down, middle, up, middle. Down, middle, up, middle. Down, middle, up, middle. I talk like a robot and have a beat, now I make $1 million. Okay? You connect the dots. And you have your sine graph. Okay? So how I change that for y equals 1/4 sine of x, notice that the 1/4 is in the A spot. The A spot is a vertical compression. We're going to call it a amplitude of 1/4. So the sine of 0 is still 0. 0 times 1/4 is still a 0. The sine of pi over 2 is 1 times 1/4. The sine of pi is 0. 0 times 1/4 is still 0. The sine of 3 pi over 2 is negative 1 times 1/4 is negative 1/4 is 0. And you see it follows the exact same pattern, it's just 1/4 as tall. It went up, middle, down, middle. So I will go down, middle, up, middle. Connect the dots. And you get 2 sine graphs on the same coordinate axes with different amplitudes. And because they have different amplitudes, you can physically see the compression between them. Okay? Also, your graphs are going to look really cool and people are going to see your work and they're going to think you're super smart because the graphs look really cool. Okay? Now that's a sine graph. I'm going to come down here, and I know there's 3 of them. I'm going to do one of the cosine graphs. I will do 1c, because now it's a amplitude increase. I don't see anything changed in terms of B or C or D. So I don't have a period change. I don't have a phase shift. I don't have a vertical shift. It is just the amplitude change, which means the period is still 2 pi. So I start at 0, I go out to 2 pi. I go back to 2 pi. There's 4 boxes, 4 sections or intervals in between 0 and 2 pi. So take 2 pi times a quarter and go by pi over 2 increments. Pi over 2, pi, 3 pi over 2. Negative pi over 2, negative pi, negative 3 pi over 2. Take a look at your 2 amplitudes. What's the highest I'm going to need to go between the 2 graphs? The lowest I'll need to go between the 2 graphs. Okay? So I'm going to label my axes so that I can fit both of them on there. I'll go up to 2 and down to negative 2 with 0 in the middle. Then, cosine of x. What is the cosine of 0? Uno. The cosine of pi over 2. 0. Cosine of pi. You start to see the pattern, right? It's still that same pattern of up, middle, down, middle, up, middle, down, middle, where it's 1, 0, negative 1, 0, 1, 0, negative 1, 0. Okay? So when I come back this way, if I went to negative pi over 2, you look down at 270. It's 0. Keep going the other way to negative pi. You're at negative 1. You're at 0. You're at 1. Connect the dots and cosine graph looks identical to sine. It's just a pi over 2 shift. Specifically, it's a 1/4 period shift. And then 2 cosine of x. You take all those values and multiply them by 2. 1 times 2 is 2. 0 times 2 is still 0. Negative 1 times 2 is negative 2. Is 0. Is 2. Is 0. Is negative 2. Is 0. Is 2. And you connect the dots. Notice, I am doing my best to keep these curvy. If I see a graph that's this, y'all, it's a sine wave, not Bart Simpson's head. Okay? Try to keep it curvy, please. I understand not everyone's an artiste, but try. Okay? So, I did one sine, one cosine. I did one stretch, I did one compression. Your turn. A and B. And try to keep them curvy. And most of yours are looking good. There's a handful of you, I literally get heart palpitations looking at it because it looks like the heart monitor if I have the heart palpitations. Me too. The last 3 years have been rough, dude. My kids are too young to understand when I say, you understand that I'm going to have a heart attack before you graduate? My wife says I should stop that.
My dad blames all his gray hairs on us.
I used to sit behind my mom while she had breakfast, picking at her gray hairs, saying, I did that, I did that, I did that. Yeah, I'm going to hell. And your dad is 100% correct. My wife developed gray hairs by 35, 36 because of our child. But the periods on these are the same, from negative 2 pi over to 2 pi. That won't change yet.
What makes that change? What makes that change?
If I change b, because now I'm taking my input of pi over 2 and I'm multiplying it by something. So when it would have been pi over 2, 1, what happens when I take that times a half? Well, now it's not going to get there until twice as long because I'm cutting my input in half. So now it'll go out to pi 1. It'll stretch it, just like with all of our other transformations.
I was doing the one down here, I'm like, what is the negative 2? That's wrong.
Welcome back. Okay, the x-axis will not change yet. Nothing in the B or C spots. So you label it in pi over 2 increments because that's 1/4 of the period. From negative 2 pi out to 2 pi, so we have 2 periods of our graph. How you label your y-axis depends on how you want to fit the 2 functions. Maybe you cut each vertical box up into fifths. Maybe you cut them in half and go a little bit off-road. Okay, you get a choice. Okay. If I have cosine of x and 1/3 cosine of x, I need one of them to be 1/3 the size of the other. So personally, the way that I'm going to do this, is I'm going to chop these up in half, like so, and then say each one is 1/3. Would that work? 1/3, 2/3, 1. So if I do that and say this is going by 1/3, I could just put right next to this 1. Put next to this -1. And then connect the dots. Cosine of x, cosine of 0 is 1. And then follow your pattern. Down, middle, or middle, down, middle, up. Middle, down, middle, up. And your 1/3 cosine of x is just going to be 1/3 of that height. 1/3, 0, -1/3, 0, 1/3, or middle, down, middle, up. There you go. Okay. Sine of x. Given the space that I have to work with, what I'm going to do is call this 1, 2, 3, 4, and just at the edge, 5. 1, 2, 3, 4, just at the edge, -5. Okay? And then sine of x. The sine of 0 is 0. The sine of pi over 2 is 1. And I go middle, down, middle, up. Middle, down, middle, up. Connect the dots. And who else? We need a different color. Orange. I go all the way up to 5. So the sine of 0 is still 0, but the sine of pi over 2 is normally 1. Now it's 5. Middle, down, middle, up. Middle, down, middle, up. And you can see that 5 times stretch to it. Okay? Now the further we get along in these, right now, because it's only a vertical stretch, or sorry, an amplitude change, it's okay to put them on the same set of axes. It's actually not the big deal. But the second I start messing around with the period and the phase shift, I'm going to say, screw it, just make separate graphs, because they're going to start getting nasty. Okay. All right. Next up, they're taking it in baby steps because these are whole new kind of graphs. What do you think that's going to do? Vertical reflection and a vertical stretch. So nothing has changed in terms of the period. I'm still going from -2 pi, -3 pi over 2, negative pi over 2, 0, pi over 2, pi, 3 pi over 2, 2 pi, no kidding, my pi. And how do you want to label your vertical axis if I want to fit both of these? Do you want to say this is 1, 2, and go off-road for 3? Or do you want to say this is 1/3, or sorry, 1, 2, 3, 4, go by 2s? Doesn't matter, right? Either I compress it into that space or I go a little bit off-road. Your choice. Normally I would compress it into this space, but I'm going to see if I can go off-road and make it not suck. So here's 1, 2, off-road 3. Here's -1, -2, -3 off-road. It's just a little bit off-road. It's like the kids in the Hick lot who drive on a gravel road and think that's off-roading. Okay. So the cosine of x, cosine of 0 is what? 1. So I start my cosine graphs at the maximum. And then x-intercept, minimum, x-intercept, maximum. Because it follows that pattern of middle, down, middle, up. Connect the dots, try to keep it curvy. And I move over to womp. So now, 3 times as tall, so I'm not starting at 1, I'm starting at 3, and reflected. So we're actually going to start at a minimum of 3, but then 0 times negative 3 is still 0. Negative 1 times negative 3 is now positive 3. Get down here. Okay, and it still follows that pattern of down, middle, up, middle, down, middle, up, middle, down. Connect the dots. Okay. And then it looks like a really angry wiener dog. More like a mouse? Yeah. I see the big floppy ears. Yeah. So. Okay. So, both of them involve a reflection. One is sine, one is cosine. One is a stretch, one is a compression. Can you do it? Again, we haven't messed with the period yet. It's still negative 2 pi to 2 pi. I should say, it's from 0 to 2 pi, but we have 2 periods of it shown. Okay. I'd recommend labeling your axes and then check with a neighbor. Make sure that you got the same idea. Then put your graph on there. You don't want to get caught out in the open with you have your graph already done. It turns out, oops, I backwardsed it. Okay. Oh, no. Okay. Okay, looks like we're doing pretty good here. Now, I know that some of you really despise having your graph cluttered up. especially if you have maybe not the nicest handwriting, because then you can't even tell what's going on. So one way that I have seen kids do this in the past is they label on the outside of the box instead of directly on the axes. So they'll put negative 2 pi, negative 3 pi over 2, negative pi over 2, 0, pi over 2, pi, 3 pi over 2, and 2 pi right there. If I need to go 1 and 1/5, maybe I'm going to label this as 1. Here's 4/5, 3/5, 2/5, 1/5, 0, like that, where I'm breaking up my vertical axis like this. I'll say negative 2/5, negative 4/5, negative 5/5, or negative 1. So I've seen kids do that too, where they just don't like having all the stuff on the graph, so they'll label on the outsides of the graph instead. You still have them on your vertical and horizontal lines. You can still tell where they go. But for some kids, that is just the jam. Okay? And then I'll label my cosine goes from 1 to 0 to negative 1 to 0 to 1 to 0 to negative 1 to 0 to 1. And 1/5 of that, negative. Don't forget that part. So instead of being up at 1, I'm going to be at negative 1/5. And then follow the same pattern of middle up, middle down. Middle up, middle down. Connect the dots. How'd we do? All right. Okay. And then I'm going to cheat. I win. And we need to go to plus or minus negative, or plus or minus 4. So I'm going to say 4 is up here, negative 4 is here. Just go by 2's. So 2, negative 2, 0 in the middle. And we'll say sine of x. The sine of 0 is 0. The sine of pi over 2 is 1. Poke, 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 poke. Because it is down middle, up middle. Versus negative 4 times that. So negative 4 times 0 is still 0, but negative 4 times 1 is now negative 4. Is 0, is positive 4, is 0. Is positive 4, is 0, is negative 4, is 0. Connect the dots. Don't they look cool? Like, they just look cool. You feel smart doing it. There's like pies and like fractions and negatives and curves, and they overlap and it looks like a DNA helix, and just good stuff. All right. Talk to me, Goose. Show me thumbs. How you feeling about it so far? Okay. Well, you know that's how it works. Make it harder, right? Like, it always gets harder after example 1 and 2. I want to do one more. And let's see if you can, instead of going to plus or minus 2 pi, which is 2 periods, a period can go forwards or backwards. It's just a amount of space. So I could go from 0 to 2 pi and then again out to 4 pi. Can you put these two on here? The axes are already made for you. Can you fit it to someone else's axes? Okay, so now instead of showing a positive and negative period, they're just going to show two positive periods. Same difference. Yeah, I'm sure on quiz day next week we're going to have a handful of kids sounding like transistor radios. At least the ones who can whistle.
Oh god. Sorry, dude, this one is
Took me to my mid-20s before I figured out how to whistle.
I can't whistle
I
with
couldn't
two
whistle at all.
fingers.
I can't do the
That's
finger thing either.
ever. Lightningberg can do that.
Yeah, when you see someone do the whole like Spider-Man thing and just like rip your eardrums out. Oh, never been able to.
Yeah, like the little claw thing.
Yeah. Okay, the axes are already there. Hey, what if instead of this, what if I was there and had 0 out to 2 pi and negative 2 pi? Cosine starts at the maximum, middle, down, middle, up, middle, down, middle, up. This is a periodic function. That's what it would have been if it went from negative 2 pi to 2 pi. The only difference is now I didn't start in the middle. I started at my maximum and still kept going. Okay? And then 1/4 of that with a negative means I'll start itty bitty right there. Like at the tips of these little tick marks. Okay? Good? I saw a couple of you are a little hesitant, but all right. Womp, womp, womp. Okay. Now we're going to start messing with the period. Okay. Period and frequency are reciprocals of each other. A period is how long does it take to repeat itself? The frequency is how long does it take to complete or how many cycles are in this space? Okay, so period is how long to complete one cycle, or how long, how far, whatever distance, versus the frequency, you just flip it. And it says this many cycles in a particular distance. So the easiest one to do is if you're working with 2 pi. A period would be how long until I repeat myself? There is one cycle in between 0 and 2 pi. Frequency flops it and says how many cycles are in this distance. It is literally 2 pi over b versus b over 2 pi. They're reciprocals of each other. Okay? How far to complete one cycle? How many cycles in this space? That's why FM radio, frequency modulation, talks about how many cycles are in this space. So they'll say, oh, God, it's been like 20 years. It's been like 20 years. The standard units for, not hertz, right? So when they'll say like at this frequency is at so many megahertz, right? They're saying in this space there's that many cycles. It's happening that many times in that hertz, in that space. So when they say so many megahertz, they're saying I'm compressing this many millions, right? Millions or thousands of waves into this physical space. Anyone got a old school radio? No digital. Tune that knob, right? Do you know why that is? Anyone ever talk to you about that in physical science when you're talking about the waves? There's a coil of wire inside the old radios, and it literally takes that coil and it expands it or compresses it so that it lines up with the size of the wave. So when the wave hits all those coils at the same time, here comes sound. Now everything's got digital to it. You have digital instead. But that was the genesis of all of your much loved technology. Who got Wordle today? No? Mac's still working on it? Okay. So, notice that with the period, it was always 2 pi over absolute value of b, and it was absolute value of b over 2 pi for the frequency. In our book, we are just introducing trig functions. B is always going to be positive anyway. Okay? When you move on to trig next year with Mr. Spear, okay, now you'll deal with a negative. All right. Describe how these are related. So first up, the cosine of x has a 1 in the b spot. That means the period is 2 pi over 1. So just 2 pi. What the book will not ask you for, but I'm going to tell you, start writing it down because that's how we make our graphs, is my quarter marks. Remember, that's where the relevant features were. We didn't just write 0 and 2 pi. We wrote 0, pi over 2, pi, 3 pi over 2, 2 pi. We wrote out the quarter marks of that period. So I take 2 pi times 1/4 and get, this graph is going to go by pi over 2 increments. This graph, on the other hand, cosine of x over 3. The period is 2 pi over b. What is b? Which is what? 1/3. B is 1/3, right? This is cosine of 1/3 x. So if b is 1/3, dividing by fractions is easy as pi. The period is actually 6 pi. So all of the boxes on this graph, all of the tick marks where the relevant features are, my quarter marks, what is 6 pi times 1/4. 3/2. You can see that one graph is literally going to be stretched out 3 times as far as the other. We've talked about this before. If B is 1/3, then the graph stretches 3 times as far. How many of you have that job? You're saving up for something. I'm going to save up for a car. I even got my parents said they're going to match me. If the car that I want is $4,000, I'm going to save up $2,000, and then they're going to match me, and I'm going to get my car, and it's going to be great. I've got this far until I saved up for it, and then they say, oh, but 1/3 of your paycheck needs to go into savings, and 1/3 of it you're going to have to use for your current bills, like your current gas, your current car insurance, your current cell phone bill. So only 1/3 of your paycheck is going to go into savings. It now takes 3 times longer to get where you're going, right? So that's why it has that opposite effect. So when I put these on the graph over here, if I want them both on the same scale, then I need to go out to, I'm going to use orange because that'll show up. I need to go to the furthest, to the biggest period. So I'm going to go from 0 out to 6 pi and back to -6 pi. And then I'm just going to have to fit the smaller one into this scale. We said we're going to go by 3 pi over 2 increments. So 0, 3 pi over 2, 6 pi over 2 is how much? 9 pi over 2, 12 pi over 2, which is 6 pi. So I know I did it right. What about the amplitude on both? Do I need to mess with my vertical axes? Okay. Just so I can see more of my graph, I am going to put my 1 and -1 here. It'll just be a little easier to see. Okay. So let's go put blue graph on here. Cosine of 0 is what? Okay. So I always start at the maximum, and then I will follow my pattern of middle, down, middle, up. Because if I put 3 pi over 2 right here, 3 pi over 2 times 1/3 is pi over 2. Cosine of pi over 2 is 0. Okay, so instead of having to fit this to someone else's scale, I'm just making the scale work for me. And then middle down, middle up. To fit the other one, I ask the question, how many of these quarter marks fit in those quarter marks? So I'm going to go to all of my little boxes here, and I'm going to put 1, 2 tick marks in there, 1, 2 tick marks in there, 1, 2 tick marks, 1, 2, 1, 2, because now it's broken into thirds. And now that it's broken into thirds, I'm going to follow that same up, middle, down, middle, except it's going to be at all of those little tick marks instead. So cosine of 0 is 0, and then middle, go to the next tick mark, down. Go to the next tick mark, up. Next tick mark, up, middle. Down, middle. Up, middle. Down, middle. Up. At all of those 1/3 marks, you're pretending those are the boxes now. Okay? And then middle, down, middle, up. Middle, down, middle, up. Middle, down, middle, up. And when you connect those dots, you should see something that happens 3 times as much as our blue graph. Look at where they hit the same point. Look at where one graph hit the other graph. Where did the x-intercepts line up, or the maximums or the minimums line up? At 0? Where else? I heard someone say it. Plus or minus 3 pi, plus or minus 6 pi. That isn't a coincidence, because one is 1/3 the size of the other. Okay? Do you see why trying to put two graphs on the same axis might be a bit of a pain?
Yes.
What if I told you instead I would like you to make two separate graphs and just label the axes differently? Sound good? Now, I got to look at the next problems, though, to make sure whether it's bad enough that we have to do that. Ah ha ha! No. That's a 3x. You know what? Let's try one of them. Let's just try 3a, and then we'll call it a day. But I want to make sure that you can do it when it's not difficult. Put these graphs on the same axis. One is 1/2 the size of the other instead of 1/3. This one will not be bad. Too bad.
I know he knows that saying.
What do I know?
I'm sorry, Miss Grandpa. That's too damn bad. Do you know what that's from?
No.
It's from Holes.
Oh, it's probably been 17, 18 years since I've watched that.
I guess people still watch that.
When I ran the group home in Arizona, the boys watched that movie in their like 8th grade English class or whatever it was. And then they became obsessed with digging holes.
Oh no!
One of them just said, "I want to dig a hole."
Oh boy. Wait, how did we get the corner?
Period times 1/4. A month later, the back of the yard was a human-sized prairie dog town with tunnels, 6-foot deep holes. We got in trouble with the head of the company because they found the gas main for the neighborhood. Oh, it was amazing. The boys would come home and rip through their chores, and they were all like the best behaved month they've ever had because they all wanted to go outside and continue working on their project. I'm talking about an area almost the size of the Commons with 3 to 7 foot deep holes, access tunnels, arches, you name it. They just went out there and dug for a month.
I'd love to do that.
And then on a good clear night where there was a full moon, if they earned it before bed, they would go outside. They called it ninja seek. Basically hide and seek in the dark with nothing but moonlight. It was actually really cool. Okay, what you should have is oh, that one's kind of messed up. And then the other one's going to be half the period, so middle, down, middle, up, down, middle, up, middle, down, middle, up, middle, down. Eh. Should look like that when you're done. Without the detour over there. I put the dot in the wrong spot and didn't remember. Okay, we'll pick it up tomorrow. I don't know if we'll finish all of 4.4. I hope we can. Depends on how ready to go you are. Your assignment is going to be fairly small. It'll be just, I don't know, maybe 3 or 4 of these. That's it. Actually, I'll probably go include some of the stuff we missed from 4.3 now that we know our unit circle.